Hello and welcome to video lecture 5, which covers section 1.3 day 2, linear equations in two variables. As always, please take a moment to read today's objectives. To satisfy objective number 1, you need to be able to identify both parallel and perpendicular lines, whether they're on graphs or whether you have equations. Example 1 asks you to graph 3 slope-intercept equations on the Cartesian plane below. Please take a moment, pause the video, and graph those 3 lines, and then check your work with me. Well, how did you do? I've color-coded my 3 equations, y1, y2, and y3, so you can easily identify which line represents which equation. Please use these as the basis for your answers in example 1, parts B and C. Take a moment to answer those, and then check your answers with mine after you've paused the video for a moment. So what's the relationship between lines y1 and y2? Well, those are known as parallel lines, and we'll talk about what in their equations causes them to have that relationship. You may have also noticed parallel and perpendicular from the title of the section. We will use symbols, and I'll throw those in here. 2 diagonal parallel lines is the symbol you may remember from geometry to signify parallel lines. The relationship between y1 and y3 is much different. They're not parallel because they actually intersect. Now when they intersect, they actually form a 90-degree angle, and that's why we call them perpendicular. The same can be said about lines y2 and y3. So perpendicular, if we're going to use a symbol for that, we use this symbol, which kind of looks like an upside down T. So from here on out, instead of using the words parallel or perpendicular, you can use those symbols. Let's go on and talk about part C. Take a second to observe the 3 equations given and see if you can determine what in those equations is responsible for causing these lines to be parallel or perpendicular. Did you say slope? If so, you're correct. The 2 lines that are parallel happen to have the same slope, while the lines that intersect actually have reciprocal slopes and opposite signs. So that leads us to our 2 definitions for this lesson, parallel lines and perpendicular lines. As you may already know, parallel lines are 2 or more distinct lines that never intersect. They will not cross each other's paths. How do you know if they have an equation or you're looking at their equations? Their slopes must be equal. So if you've noticed, I've written that in symbols, and what I mean by this, m1 equals m2, is the slope of the first line equals the slope of the second line, which would equal the slope of the third line, and so on and so forth. And depending on how many lines there are, we've generalized here and said m of n. So who knows how many lines there could be that are parallel to one another. The next definition is perpendicular lines, and those are defined to be 2 lines that do intersect, and they do so in such a manner that they create 4 90-degree angles. When looking at the equations of 2 lines, if you notice their slopes are negative reciprocals of each other, then they must be perpendicular. Here is the symbol notation to describe perpendicular lines with their slopes, and let me give you an example with some numbers to help make this a little more clear. So suppose the slope of my first line was 3. Well, according to this, the slope of the perpendicular line would have to be -1 over that 3. So notice what happens. Reciprocal is a fancy word for flip. So notice the slopes will be flipped. One will be negative and one will be positive. Example 2 asks us to find a slope-intercept form equation that fits the given conditions. I will try example 2b with you, and then I'd like you to pause the video and try examples 2a and c. So for b it says, find a slope-intercept form equation that passes through -4, 1 and is perpendicular to the equation given. Well, to get a better idea of its slope, we're going to need y by itself. So we're going to get this equation into slope-intercept form first, and I've shown you that here. I first move the 5x to the right side by subtracting it, and then I divide everything by -3, and my resulting slope-intercept form equation is shown here. Now, by y by itself, I now can easily identify the slope. Well, if I'm trying to find a perpendicular line to that equation, I know that the slopes of perpendicular lines are negative reciprocals. So right away, I don't have to do anything to find the slope. Rather, I'll know by definition that a perpendicular line will have to have a negative reciprocal slope. So that leaves us with y equals negative 3/5 x plus b. Next, we'll try and find its y-intercept. At this stage, this problem becomes very similar to what you have already done. We have found the slope, and remember, when finding equations given 2 points, you would then take either one of the points and plug it into the equation to find your y-intercept. Well, this is a little bit easier in the sense we don't have a choice. We have to choose -4 and 1 to plug in. So I will choose -4 and I plugged it in for x. I took 1 and I plugged it in for y, and now I will solve for b. One thing I will note is when you're multiplying -4 times 3/5, if you remember, you can make -4 a fraction and then you can multiply straight across. So this would become 1 equals positive 12 over 5 plus b. Now I will subtract 12/5 on both sides, and that will give me b alone. So the last thing I would do is combine these two fractions by making 1 simply 5 over 5. Now they have a common denominator. 5 minus 12 is -7. So b, the y-intercept, is -7 over 5. Now we'll put everything together, and our final answer would be y equals -3/5 x minus 7/5. So this is our final answer, and I know I have several things boxed here, but what I'm starring now is our answer. And notice its slope compared to the original slope of the first equation. Notice they are not the same because we wanted these lines to be perpendicular. So be careful. They're not always going to be perpendicular. If you look in A and C, those are parallel. So try A and C, pause the video, and then check your answers tomorrow when you come into class. The final two examples in this video lecture are linear applications, or word problems that ask you to apply what you've learned to a real-world situation. So I'll get you started on both examples 3 and 4, and then I'd ask that you finish them, and then of course we'll check them tomorrow in class. So example 3 says, when driving down a mountainside, you notice warning signs indicating that the road has a grade of 12%. This means that the slope of the road is -12 over 100. Approximate the amount of horizontal change in your position if you note from elevation markers that you have descended 2,000 feet vertically. Draw a picture to help. So I'll start by drawing a picture to give you some better idea, and then I'd ask that you finish the problem on your own. So hopefully from the reading you've inferred that the driver is going downhill. So I've drawn a little picture on the left that indicates the starting position and the current position of the driver. Now if you look at the slope, it's -12 over 100, and using our rise and run definitions, we can then say that for every 100 feet the driver moves horizontally, he or she will descend or go down 12 feet. And that's going to be consistent each and every time because of the slope being the same. Now, the question being asked is, what if the driver's still going downhill, but the driver has descended 2,000 feet? So if the driver descends 2,000 feet, what then must be the driver's horizontal change? See if you can take what I've done and finish the problem. Example 4 deals with depreciation, or the decrease in a vehicle's value over time. It says a person purchases a car for $25,290. After 11 years, the car will have to be replaced. Its value at that time is expected to be at $1,200. 4a is asking us to take this information and write a linear equation. Well, there are two things that are changing in this problem. That would be the value of the car and, of course, time. If you remember what we said in the last video lecture, remember you want to try and take those variables and say this phrase both ways and see which one sounds better. In this case, it clearly sounds better that value must depend on the time. Therefore, value is our y, or dependent variable, and time will be our x. So the equation that we are trying to write will look like v equals mt plus b, and we need to find the values of m and b. Well, to do that, we're going to need some points. So if you look at the problem, it says 11 years down the road after owning this car, it's going to be worth $1,200. Well, if value depends on time, time must be our x coordinates and value must be our y. So that being said, I can take the 11 years and $1,200 and put them into an ordered pair. That would look like 11, comma, 1,200. The problem also states that we purchased this car for $25,290, and we did this at the very beginning of this process. So if we're looking for a time or a year there, we're going to put time 0, even though that it's not explicitly stated. We imply that because that's the first time that we had the car. So the ordered pair would be 0, comma, 25,290, and now what we have are two ordered pairs that we can use to write the rest of our equation. So please take a moment to finish example 4a and 4b and check your answers tomorrow when you get to class. Well, this concludes video lecture number 5. Please take a moment to look back and write down at least one question you have after watching the video lecture. We'll see you in class tomorrow, and good luck.